will be up on Canvas, and I'll show you that. Our objective today is to report evidence of energy transformations in a chemical reaction, and that's the state core if you want to read it. We're going to lecture on thermochemistry, and then 7.1 is due next time. So we were able to finish that fairly easy last period. Now, as you go in, you need to make sure that you choose Chemistry Spring, okay? That's the one that you want to go into if you didn't already. As you go in, I will always have the units up there that are there. There will be your quizzes, but there will also be a daily schedule. Okay, this is going to be important to you because underneath daily schedule, this is where you can go if you're sick or you're going to be gone a day. I have got the whole unit in here for you and what we're doing and when the test is. So you can see right away what we're doing and when the test is. So if you forgot your homework and it's at school and you need to get done for next time, you can click here and bring up and print the pages you need. The guided notes are here. The objectives are here. As we finish a lecture, I will put it up here and link it so that you can go and listen to the lecture. If you were absent or you were sick or whatever, you can take the notes and be right up where you need to be when you come back. Okay, or if you missed something in the lecture and you need to go back and see it, you can do that. All right. If we have a lab, I will hot link, and it'll hot link to a lab page where you can download the lab if you've left your lab notebook, and we'll also put makeup labs in that way, also there. Okay. So that's just a little bit of how that's going to work. On Canvas, all I'm doing is having your quizzes, so your full grade is not going to be on Canvas; it will be on Encore. Okay. But you can check your quiz grades on there. All right. You can also go to my website that's linked through Northridge, and it has a whole year schedule of what we're doing all during the year. It would be first day all classes is the tab you would click, and then general chem. All right. So let's get going with today. So your green packet is the one with the notes. So if you grab that out, and let's start with the notes. Thermochemistry is a little bit of fun. It's working with heat. For some of it, how heat comes in and out of things. We're not just going to be working with heat in this unit, though. We're going to be working with energy. So the first thing we're going to look at is a little bit of a review of lab safety. We're going to watch a little video here. I am going to turn off the recording during the video because for some reason the recording does not like the video, but I will put those videos up on Canvas so you can watch them. What I want you to do is I want you to watch this, and on the back of your green sheet, I want you to list all the safety violations that this person is doing. This instructor is not very smart, and I want you to tell me everything he does wrong as far as safety goes. Okay, so again, I'm pausing the video. This will be on. Let's talk about some of the safety violations that he had. Who's got one? Yes?
Walking with fire,
Yep, what else?
Oh, he had no safety belt.
Big one, yes.
He spread molten iron throughout the classroom.
And started a fire, yes.
He didn't have gloves either.
He didn't have gloves either, and molten iron is like 3,000 degrees Celsius.
Friend's candle.
Yeah. Yeah, he had to say put out the fire. Really? Oh my heck.
When he was lighting the blowtorch, he was really close to a kid.
Yeah, when he was lighting the blowtorch, he was in the corner, but he was right next to a kid while he was lighting the blowtorch. Did you see that? That was awesome. Yeah. He wasn't very careful at all. This this reaction gives off a lot of carbon monoxide too. Not to be done inside. And if you notice that molten iron, all these are now holes. Whoops, let me go back. Whoops. All those things that you saw on the bottom, those were holes in the floor. It's 3,000 degrees. It's going to burn a hole in whatever it comes to. Okay? So he didn't do things very smartly, for sure. And he did a bigger amount than he should have done. If he did it inside, it should have been a very small amount. But what he did was so big that it just spread everywhere. So he was lucky he didn't start that whole thing on fire. I don't know. This is up on YouTube as Lab Stupidity. So, Okay, so let's go forward and talk a little bit. So as we do different labs, we're going to be talking about you really need to do this, you really need to do this. And as we do those labs, please follow the safety things.
If you're going grams to moles, is it like the full thing?
No, you don't do the last one. We'll talk about that in a minute. Okay, let's come back to here. So two main types of energy that we're going to talk about today, potential and kinetic. Looking at this picture, who can tell me what potential would be? Yes? Buildup of energy. Okay, anybody have another way to phrase it besides that, the buildup of energy? Energy that's not moving. Okay, what else? Yes?
It's stored.
Energy that's stored. Okay, so all those together somehow come up with something you're going to put down for potential energy. How would you describe it by what these guys have said? Because it is stored energy. Up here at the top, I have potential energy. I'm not moving, but I have the potential to move, right? Okay, so now give me a definition for kinetic energy. Energy of movement. Yep, energy of some kind of movement. So he has kinetic energy here. He has kinetic energy as he's climbing the stairs, but at the top, he's got potential energy. Yeah, well, you never know. Okay, so we have a unit of energy that we use. So hopefully you've written down something for potential energy and something for kinetic. Basically, potential is stored energy and kinetic is energy of movement. For units of energy, we use the joule. Now, probably some of you have said, well, we use calories. Yeah, calories are used as nutritional amounts, and usually when we talk about nutritional calories, that is actually a kilocalorie. So when you say 180 calories, this cereal is 180 calories, it's actually times 1,000 in calories that we would use in lab. But calories are an English unit, and we like to use the System International, and that unit is joules. So we're going to be using joules here. And 1 joule, and you'll want to know how to spell joule too, that's why I highlighted in blue or purple, whatever you want to see that color is. 1 joule is actually equal to 1 kilogram times a meter second divided by a second squared. Okay, so when we get that, we have a joule. And down there at the bottom, we've got a conversion between lab calories and joules. Now, remember that a nutritional calorie is 1,000 lab calories. But our body needs that many calories to work. Our body is a machine that eats calories, needs energy to move. So we need to make sure we know these units of energy. Has everybody got that down? Okay. All right, so then we're going to go forward and we're going to talk about some energy can appear in many different ways. I'm going to show you a few and then I'm going to have you pair share. So I have these little cars. My little grandkids love these little cars. You know, the kind that you pull back and then you let go and it's supposed to go forward. That one didn't do very well. Okay, so as I pull it back, what kind of energy is it? It's kinetic because it's moving. But when I stop, what is it? Potential, and then I let go. It's supposed to be kinetic when I let go because it's supposed to go. I think I've wound that too many times and it's down underneath. We'll go with it later. Okay, here I have a flashlight. What kind of energy do I have right now? Potential, and when I click it, it is kinetic. I'm giving you light energy right now. Okay? I'm giving you light energy. There's actually light waves that are coming off of this. When I stop it, there's no light waves. Okay, so there is energy, but it is in the form of light. Okay, so we had motion energy, or kinetic energy. Okay, here I've got something else. Why'd you guys go, oh no? What is this? It's an air horn. So what kind of energy do I have right now? Potential, and it's not that loud. Okay, kinetic, it's almost out of juice. Okay, so I want you to pair share for the next 5 minutes. I want you to have at least 2 things under each of these that you can tell me as a potential and kinetic, something that would work here. Okay, I gave you 3 and you can figure out where they go, but I want you to pair share. So I've got some singlets here. Let's have you 2 share, and can I have you run back there to that one that's empty? See how there's an empty one? I'm going to have you pair share there. So I'm going to bring up a timer. Okay, let's go back to this. Who has some really good examples for temperature? Yes? A lighter, okay?
Rubbing your hands together.
Rubbing your hands together, okay, friction. Anybody else have a good one for temperature? Yes? No? Okay. Yes?
A heater.
A heater. Okay, what about sound? Who has some good examples for sound? Yes? Instruments, okay? Your voice is an instrument, good. Okay, any others for sound? A clap, okay, potential, kinetic. Okay, what else? A speaker, yes. Phone. Okay, what about light waves? Yes. The sun, okay, what else? Fire. Flashlight. Anybody else for light? Light switch. Okay, that can also work in electric, right? Okay, what about electric? Electric kettle. Toaster, a phone. What else? Tesla machine. A light what? Lightning, okay. How about chemical? What do we have for chemical? Photosynthesis. What? Battery. Baking soda and vinegar. What? Gasoline. Glow sticks, yes. That would actually go in light and chemical. What about nuclear?
Microwave.
Bomb, a microwave. I heard something else back here. Power plants. Okay, what about elastic? Rubber band. Okay, I think about those little toy airplanes that you wind up, you know, and then you let go. Or the little thing that I had, that's a wind up of an elastic.
Wait, what a balloon?
Mm. We're not going to go there right now. Okay, mechanical. We don't have that. Did anybody put anything down for mechanical? I know you don't have it, but did anybody put anything? Yes. Car engine. Okay, before it starts, it's a pendulum. Yep, before it lets go, right? Okay. All right, let's go forward. We're going to watch a couple of energy transformations. If everybody gets done, we'll come back and watch more of this. This is an awesome thing that you can look at YouTube. It's the Royal Institute, and they actually do every year at the U of U and now at Weber State, they do demonstration times like this. If you went to the Faraday lectures at Weber State, or if you went to the U of U Science Day, or Weber State Science Day, you could see some of this stuff like this. Again, I'm going to pause the video at the end. So again, it's at the Royal Institutes, and you can bring it up on YouTube. It's pretty cool. We're going to be working with two different temperature scales, Celsius and Kelvin. To get to Kelvin, you add 273 to Celsius, 273.15. The Kelvin and the Celsius scales are both divided in the same increments. So the only difference between the Celsius and Kelvin scale is on the Kelvin scale, we've never reached zero, and we don't have a negative number. So when we do a lot of calculations, oftentimes temperature is on the bottom of those calculations. And so we can't divide by zero because that would be undefined. And if we divide by a negative number, a lot of times it doesn't make sense because we're looking for volume or we're looking for pressure. And we can have a negative pressure, but a negative volume really is nonsensical. Okay, so we have to have an absolute temperature scale so the equations that we work with in gas laws and stuff work. The change in temperature, though, in degrees Celsius and degree Kelvin would be the same. So it doesn't matter if I'm in Kelvin or Celsius if I just need the change in temperature. I can do that in either one. Okay, so a little bit of background on Celsius. To me, the Celsius scale makes a lot more sense than the Fahrenheit scale because it was done with where water freezes is 0 and where water boils is 100. And then they took and evenly divided between those, so you have 100 points. The body temperature is 37 degrees, so those are some things that you can look at to compare back and forth to go that. It is also often called centigrade instead of Celsius, and it was invented in 1742. So this is what we've done today. Okay, I'll always have an end slide so you can sort of see what we're doing. We should have completed quiz 7.1. We talked about classroom procedures. If any of you have any questions with that, please ask. We've done the objective where we talked about energy transformations and different ways they can transform. And then we've been working on the thermochemistry lecture, and 7.1 is due next time. So what I'd like to do right now is go to here and just remind you, if I have an equation, say H2 plus O2 yields H2O, what do I need to do to balance that? Just really quickly, what do I need to do to balance that? 2 in front of the H and 2 in front of the H2O. Okay, good. So we've balanced it. Now, if I have been given, say, 11.0 grams of H2, and I want to find out how many grams of O2 that I need to mix with it to get an answer, then I'm going to always start with what I'm given, right? So what I've given was the 11.0 grams of H2. Make sure that you always put what you have. What's the first step? Just a reminder, this is stoichiometry, what we just came off of. What do I put next? Yes? Okay, how many grams of H2? So there's 2 times 1.008. That's just from the periodic table, grams of H2. What do I put on top? Always 1 mole. When I'm going from grams to moles, it's always 1 mole. When I was correcting a lot of the written semester tests, a lot of kids put 2 there. Okay, you got to remember, when I'm going from grams to moles, it's always 1. So then I can come back and say, oh, grams cancel. What's my next step? From moles to moles. So at this point, I come up here and look at these numbers in front of what I want to go to and what I have. What do I put on the bottom? 2 moles H2 because I want to get rid of it. 2 moles of H2. What do I put on top? 1 mole of O2. So at this point, I can then cancel out moles of H2. Then the last step, because I'm not to grams yet, what would it be? What do I put on the bottom? 1 mole of O2 because I want to get rid of it. And what do I put on the top? Grams of O2. So I'd look up oxygen and 2 times it, it's 15.999. And then my moles of O2 would cancel, and I would times through the top, divide, parenthesis, times through the bottom, close the parentheses, and hit enter, right? I wanted to make sure that we went over this one more time because, like I said, on the semester test, as I was grading it, a lot of kids were mixing this green area up into these other areas on either side of it. You can only use, I'm going to put it in red, the ratio from the equation when I'm going from moles to moles. Okay? Only when I'm going from moles to moles. Now, on your assignment, you got some review questions. You might not start with grams all the time. You might start with moles. So then I'd cross out and I'd start here with moles and I wouldn't put anything underneath it and I'd go forward. Or maybe I stop with moles and don't finish it to grams. But the steps are the same. Okay? Questions? All right. When you finish assignment number 1, if you finish it before the end of the period, raise your hand. I'll come around and give you a stamp, and I might assign you to help somebody else that's struggling. Okay, because I'm only one person, and there's lots of you in here. All right? Last first period, we were able to get everybody done, and we were able to watch some more of the videos. So if we can do that, that would be awesome. Okay? Time? Yes. Okay, yes. You need a question too? Okay. I'm going to stop.